Theme of the day. It has to do with the flood. I imagine that you will explain a little bit more about it. You guys are ready?
We are ready.
Yes. Whenever you guys are ready, please start.
All right, thank you very much and welcome back everyone. My name is John Method, and along with my teammates, Cyrus Jan, Zahid Shazad, and Noe Hernandez, we're going to talk to you today about the flood fault circuit interrupter. Flood fault circuit interrupter, or FFCI, is a system which automates the disconnection of a location's electrical services when a flooding situation is detected. So of course we start with our motivation, and what I'm going to take you through is both our motivation, our design process, really talk about how we implemented the design that we specified, go through a little bit of cost, and then we'll get to the fun part, which is the demo at the end. But first, the motivation really is like a lot of what you've seen in many of these projects already. It really was about the recent flooding event using experience with Ryder. But more specifically, what we're trying to address is that flash flooding occurrence where people are trapped inside a home, and we're trying to then offset the risks associated with electrocution, where you've got a flood, rising waters in a home where service is still active in the location. So we then specified a design, and you see that also laid out to the side here as well. And the basic block diagram covers both remote sensors, which would detect a flood around a location, which communicate back to some kind of simple logic system. That logic system is meant to then have an independent power source, the idea being that this system could operate independently of whether outside power is still active at a location. In addition, it then communicates its statuses back to some kind of controller system. That controller system would provide the audio-visual interface to the user, as well as communicate alarm statuses back to something like what we label here generically as a transfer switch, which would then pull the location's active electrical service away, and again, remove it from active electrical service connection. So what I'd like to do next is hand this off to Cyrus Jan to talk more about the research we did on the sensors.
Hi, I will be talking about sensors today, water sensors. So there were a lot of different types of sensors, but each of them had pros and cons. And the first type of sensors that we considered were conductive sensors, which are cheap, but there was a high chance of false alarm with conductive sensors because even a small amount of moisture or a spill could send a false alarm. And the other type of sensors were capacitive, pressure, infrared, ultrasonic. But the problem with those is that they have to be powered on all the time, and they have to be active. So we decided to use mechanical float switches, which are also known as magnetic. So this picture shows the mechanism of the magnetic sensor. So as the water raises the magnets, there are two reed switches here, which are going to get magnetized, and as a result, there will be a connection, and a signal will be sent to our logic unit. Next, my team member will talk about the boxes that we created for our sensors.
Thank you, sir. We have plenty of options to choose our boxes, but we choose the Maple boxes because they are waterproof and also the weatherproof. And the dimension of these boxes we choose is 5 inches in width and length, and the depth is about 2 inches. And to protect our sensors, which are going to be inside, we choose 2 layers, inner and outer, and to protect the sensors from all the waste material, including with the water. And the outer side, we have 18-gauge steel layers, and the inner we use the fine mesh, which is the diameter is about 0.0125 inches. And for more sensors, now we'll talk about the number of sensors.
Thank you. So the question was, how many of these switches should we use? So we have to strive for a balance between cost and reliability. So we have to choose 6 of these sensors. Now having 6 of these sensors requires to have 3 boxes. So the way we designed this is that we will have the boxes outside of the building, along the wall, equidistant from each other, but most importantly, they will be placed at a height of 12 to 16 inches because that's what the usual height of our electrical outlet is. So the way we connect these boxes back to the logic and controller, we had to choose a cable that was rated for these purposes. So we chose a cable that was waterproof, weatherproof, and direct buried. And this cable has 4 conductors per bundle. Now we connect these back to the logic, and now we're going to talk about how these logics work. By John Method.
So we've got the signal now from the sensors. what do we do about them, and what states do we define to respond to those? And having selected for 6 sensors, what we then defined were 3 unique states that we want to try to communicate back. The first of these was a unique fault state. The idea being if we have stacks of 2 sensors each, what if we only get back a signal from the top 3 sensors? So we defined a special warn state that would tell you that only the top 3 sensors are active. Then we defined a general warn state for when any 3 of these 6 sensors go active. And last, most certainly not least, we defined an alarm state in which, in this case, 4 or more of the sensors have gone active. The intention being, of course, that's the state that would indicate us to switch over to the electrical service. Now, having talked out this design concept, we now have to go to our implementation stage. And the most significant choice we made in the implementation stage, which then had some downstream results in all of the elements that we've looked at in our design, was actually that control system. We could have used a Raspberry Pi or an Arduino, any kind of system, but what we actually selected was the Vista 20P control panel, an industry standard for security and fire today. So that, by selecting that system, we actually get some benefits in monitoring and other elements that it brings in, but it did require us to make some changes to our system, the first of which Cyrus will talk about.
We wanted to have more control over our sensors and its wiring, so we decided to add 2K ohm resistors at the terminals of our sensors. So by adding these resistors, we will get 3 different voltages for 3 different situations. If the switch is open, we will have the voltage of 5. If there's a cut in the wire, we will have the voltage of 12. If there's a short in the circuit or the switch is closed, we will have the voltage of 0. And it is detected by our panel, Vista 20P, and it's going to be shown on the keypads on screen. And next, my team member will talk about the switches more.
Like Cyrus mentioned earlier, that we're using the mechanical switches, and these are the switches we're going to use. And each switch has 2 level sensors, and the length of this switch is about 5 inch, and those sensors has 1 inch to flow, so they can level 2 different level of waters. And like Cyrus mentioned, to sense those 3 different stages, we have to put a resistor at the end of the terminal of this sensor. So that's what I was doing in this picture. I was just putting the resistor at the end of the sensors. And now Noe will talk about the logic thing, the kernel map.
So as mentioned before, we have 64 combinations that we need to address. While we do that, we create a corner map that represents our switches. Basically, the switch means when the switch is open, we have a 1. When the switch is closed, we have a 0. In order to save this and communicate with our system, we had to save it in some sort of memory. So we decided to choose the Zycore X1816C. This is a 2 kilobyte EEPROM, but thankfully we only need 24 of these bytes. We have to use all of it. But then to integrate this EEPROM with the rest of the circuits, we have to change the outputs from active low to active high. So basically, every one of the outputs of the zeros change to 1s, and the 1s change to 0s. And the way we programmed this device, we had to look at the lookup table, the data sheet, and we created a programming board to do all the combinations and save it to the EEPROMs. And now to talk about these devices that this is connected to, let's talk this.
So what we've now described is the security panel interface, which has a range of voltages from 0 to 12 volts, but then a standard 5-volt TTL part, which is the EEPROM part. How do we interface between those? And that's where we design in this comparator circuit that you see between here. Now, the comparator circuit that we had selected actually has an input range that can accept between 0 and 36 volts. But the intention is that on the input side of our system, monitoring the switches, we can accept a range of voltages. In this case, it would be 0 to 12 coming in from the switches. And then we can compare that to a reference voltage to understand what the switch state is and communicate that out as a standard TTL 5-volt voltage signal to the input side of the EEPROM. On the output side of the EEPROM, we then communicate one of those 3 states that we talked about earlier out to simple active-low relays. And those relays each reflect different communication states, and they are connected back into the control panel to zones which are dedicated for each of those states. Now, when the system does need to actually communicate an alarm status out, the secret sauce in our design is the shunt trip breaker. And this receives that 12-volt alarm status and is actually able to pull a breaker, a standard circuit breaker that you see pictured here, to the off position. We select 12 volts DC because the control panel that we selected already has a 12 volt DC trigger output available, so we're leveraging that in our design here. Before I get to the demo though, I should talk about system costs. Now the system, as you see demonstrated here, the price really approaches about the $300 mark to demo a one-off system. But what we looked at is how significantly the price goes down, nearly to about the $150 mark if you look at this in volume production. But what does that mean if the system costs $150? And so to give that some context, what I brought up were some similar safety systems that are available today that you consider, because these are not going to be normally something that's sold in retail, but rather something that's installed as part of, say, a new home installation or a monitored security agreement, say with an ADT or another security provider. And when you look at systems like monitored smoke and fire or a pit flood detector, which is meant to keep an elevator from lowering itself automatically into a flooded location, those price ranges are very comparable to what we think we're able to achieve with this design. So with that, now we can get to the fun part of showing how these logic state outputs are actually affected in our system. And the first one I'm going to demonstrate to you by hand is the fault state. And that's the one you heard earlier about being only the top 3 switches. And what we're going to get when I initiate that is just an audio-visual alert on the panel here. And so if I pull the panel up, it'll indicate that on the screen. We can go ahead and disarm the system now. And keep in mind that if we look inside the system, we actually have some indicators to let us know each switch status. And now that we've rearmed the system, as you can see here, I can actually show you which switch. That's an upper, that's a lower, the left side is lower, the right side is upper, and they're color-coded for each enclosure. This is the blue, these are the white. Now, if we go further, though, what I can show you now are the warn and the alarm states. And what I'll do is I'll actually add water into the system. We'll go through the warn stage. You'll hear the alarm sounding. And then as it goes to the fault or to the alarm state, we'll actually see and hear this shunt trip breaker go, and the light, which indicates the status of the service, will go off. So with that,
So that was a warn. We just need one more to the fault. There it is. Cut the power.
all right. And that is the flood fault circuit interrupter. Any questions?
So I have a question. Now you would be, so these are installed at 12 to 16 inches height, right? Now if you look at that situation, the wire is already below the plug point, right? So what happens if the wire is lying?
So that's a great question. It's sort of essentially what are risks that we accept in any height of these devices?
Yeah.
And so one of the things we researched, in fact, when we talked about that 12 to 16 inch height was what passive elements do you already select? And so in other words, if you go to a location where wire is already routed at ground level rather than being automatically raised up, you might have risks that you need to account for where you might need to lower the height of the system. And what's great is we're saying 12 to 16 inches is a specified number, but it's not a requirement. This could be lowered if the location justifies it. But obviously, if you select 12 to 16 inches as a height, then you want to ensure, I think to the point of your question, that there's no other part of the system that's lower than that and at risk. Did that make sense? Yes.
So this thing will automatically shut off the power when the flood waters rise. That's good. Will it automatically turn the power back on when the flood waters go down?
So that's another great question about our shunt trip. Now the shunt trip we selected is only equipped to turn the system off. So it can take it from on to safety to off.
Good.
There are more expensive systems that actually are available, essentially think devices with integrated motors that could switch the device, and that's just a matter of cost and implementation.
I'd almost prefer the one that just went to stayed off, because the there could be water still trapped in the walls or on the wiring in the walls or something like that, even though the flood waters have receded.
Yeah, the context, if you will, for our system, if you think about it, is really almost a residential target application where you're defaulting to off and you're just trying to resist false alarms. Answer for you?
The lifespan of your sensor here, it's got moving parts, so is it going to corrode? What's your lifespan expectancy?
That's a great question, and I kind of want to hand part of it off to each of a couple of our team members, because absolutely we sort of accept that these devices have a limited lifespan and will fail, and in part that's some of what you heard accounted for in sort of the number of devices and the material selection. So do you want to start knowing maybe?
Yeah. So because we have about 6 of these switches, we can have 2 of these switches to be fault mag. I'm saying false alarms because all we need is 4 of them to be detected in order to switch to trip the switch.
And the normal fault stage for these devices, in fact, is to fault on. That would be recorded and reported by the control system. So essentially an operator monitoring the system could see that switches are becoming faulty and might be able to say, among other things, schedule a service replacement. And for us, that's why we can balance low cost with failure modes. And then to the enclosures, I think maybe, Zahid, do you want to talk a bit about those material choices?
Yeah, I mean, we have plastic ones as well, like those PVC pipes thing. So we can use those too. But you know, when it gets too hot, the plastic might get like too hard, and then later it can broke easily. That's why we choose the metal one, because they will stay forever. Yes, you might say like it gets rusted, but there's another type of that too. Like you can just put the paint or cover it up with the other stuff, so you will protect from the rust as well.
I think we talked about it. If with infinite time, we'd be powder coating and using aluminum, but for the purposes of surviving our tests, we chose in part these materials. That answer your question?
Okay, so first of all, thank you so much for your invitation. I'm the engineering faculty member from HCC. I'm so glad to see some of my students here promoting to this level. Congratulations. You guys did a wonderful presentation.
Thank you.
So I have a couple quick questions for you guys. Number one is, for this device, I assume this is the prototype, right? So this circuit interrupter only interrupt one branch of the circuit. You are trying to really trip the main breaker in the breaker panel. Because I would assume the safety from the city, you really want to trip the entire house breaker. You need to be able to trip the main breaker, right? Is that what you have in mind, or you have something else?
We actually essentially came up with both, so it's a great question. If you look back to our original design here, we talk about how we can integrate with a panel or sub-panel. So one option, and that's really kind of what you're seeing up here, is that we're only taking one circuit offline, right? So maybe the downstairs outlets or some such. But there's really no reason why this same system couldn't be integrated with the main circuit breaker and take the entire location off. And in part, that's all about in the design, the balance for whether you want convenience or safety. And so both options are really available in this. We're just demonstrating sort of a single branch circuit, I think, to the one of your questions.
Great concept, prototype. Second question is about safety. The safety, have you considered any safety, the safety concern about your device itself by adding into the existing wiring based on the NEC, the code? So whatever you added on, probably is a good commercial add-on, right? Safety, adding the safety for the house, for the individual homeowner. But have you considered when you look into all the specifications here, did you look at the National Firemen Protection Association, NEC, whatever other thing? Can you elaborate that a little bit?
Absolutely. So NFPA, NEC, and UL listing were all things we consulted. Our system, as it stands today in the prototype mode, is only UL listed, which basically means that this breaker cannot replace an existing breaker that you'd have for a branch circuit in the home. Again, the primary limiting factor for us today in that design is really cost of what's off the shelf available. This is essentially a part that Cyrus was able to source for us through ABB, but there's no reason why a version that is both UL listed and NEC compliant as a primary circuit breaker couldn't be sourced. It's simply just not readily available for us to prototype.
Okay.
Did that answer your question, I think?
You answered my question, yeah. Really, the last one is the question is really the comment. So where is the bypass switch in case this doesn't work, cause too much trouble?
So the great news is right here, and this is the challenge today.
Sorry to ask this question.
It's a really valid point, right? And so if you think about it, how many homes today have these security panel systems in them not doing anything? This could be actually value-added functionality that you could bring in. But the great news is what the security panel also gave us was the opportunity to arm or disarm the system if we so chose, so that essentially the system wouldn't ever go off or on depending upon your requirements.
So my question is no disrespect for your wonderful design, because I was asked this question on my first job as a first EE design engineer on my first project. I was so happy presenting to the field. the field engineer sitting there, all wonderful, nodding the head, one of the operators sitting in the back of the room, he's like, whatever, 35 years with the company, right? I was only 25. He said, sir, wonderful presentation. Where's the bypass switch? I spent 2 hours on this. You want bypass switch? And then the guy, so the lesson learned I had still remember this, right? Is whatever you guys coming out from engineering, we will trust you until we test it. So I need to have a bypass switch to keep my operation working continuously, right? So again, great project, great concept, great work. Thank you.
Thank you so much.
Any other questions?
Have you tested it, or what do you think of, okay, what kind of water are you using there?
Oh, this is truly just tap water.
Okay, so think about this. What's in floodwater?
Oh, absolutely. Yeah, garbage and slush.
Yeah, so think about, you know, incredibly dirty water with leaves and on the mild end leaves and twigs and things like that. So you're going to get some really nasty water in there. Is that going to interfere with the function of your device?
So there's two things we accounted for, and certainly that's, I want to hand it to Zahid to talk about the basic filtering that we built in. That's the 2-layer filtering. If you want to mention that one
Sure.
again.
So like you can see, there's one outside and there's one inside. If you can see the close, they're meshed in it, and we have a cover to cover it from the front. And we didn't put it on because so you guys can see when it's go up and down.
Yeah, this is for visibility. So if you came up closer, you might be able to see kind of how it's.
So it would be enclosed and have a filter in there. Okay,
That's
gotcha.
correct, and it's minimal because in part the other good news about these float switches, as long as any liquid gets in there, they're very reactive. There's not a lot of resistive force to floating those switches. So as long as we can get some water in there, which again filters through the 2 layers that were designed in the system,
Is the
we filter
filter
fine.
too good? Because if the filter's too good, then not enough water will be able to get in there to actually float the thing.
Our design is fairly porous, I think. It's meant to keep out, the idea is the mechanical protection keeps your lawn guy's weed eater out, and the filtering protection keeps all the other fun particulate out. There was
Yes, I do. A question I have as far as your system, would it be able to detect internal flooding? So let's say you were in a hurricane and you live on a hill, and that doesn't preclude you from house flooding, because the wonderful thing about hurricanes is trees like to fall on your house. And I've known people who stay in their houses even though trees fall on their house. Granted, they shouldn't. But in such a case, would you still be able to protect that sort of fool from themselves when their house is flooding, but not on the outside and only on the inside?
So the first circuit, that's a really good question because it goes to sort of the applicability of the system across a lot of different designs, which I think is there. Now, the first circuit you heard from Cyrus was actually essentially that conductive sensor. That's typically used indoors because the idea is you don't mind a false alarm for water indoors, because why do you have water indoors? And so in other words, our system we designed with these complex float switches relative to that design is that, well, we do expect humidity and water outdoors, just not enough to float a switch. So indoors, you might accept, say, a simpler design that might be more reactive because the intent is that you should less commonly see water. Could you still use it though? Absolutely. In fact, you might use fewer switches because why would a float switch ever be moving indoors versus out? And that's where Noe kind of highlighted sort of the idea that, well, you could have one float switch inside. Why should it ever go up if it's inside the house, right? Or 2 maybe, instead of a network of 6.
Mm-hmm.
That sort of answer your question,
Yes,
I think?
thank you.
I have one question. No, I like the presentation, but another thing that, coming back to that same deal, we are used here in Houston to have nothing underneath. There is a lot of houses up north that they take, especially in Canada, that they have a deep downstairs, where actually they are more subject to actually internal flooding than external flooding. So that's another way to look at it. Well, here in Houston, we might not use it. In some other locations, it's a very good idea just to control water damage inside. And the second thing is maybe from the South American mentality. What happens if you just strip the thing yourself? You have complete access to your house because you already killed every single electrical alarm or anything else. So somebody, okay, just strip it. No more power in the house. We can do whatever we want. So from the security, not from the safety, but from the security point of view, it might be also good that if somebody break the mesh or somebody, it's not just a flood, somebody actually winning this, break the thing, just to have an alarm saying, okay, this is not a flood, this is somebody messing.
Yeah, actually, what's great about that in sort of what I described earlier, which was integrating this Vista 20p control panel. It has the ability to integrate tamper sensors in addition. That'd be just, for us, an extra set of wires to get to each box. And we could literally do that kind of monitoring because it's already baked in to the controller that we set up. We're really underutilizing, honestly, that 20p and its ability to do that. But that's, again, things like disabling the system and monitoring the safety of the boxes. Thankfully, we get all those baked in with what's essentially a $40 control system.
Thank you, the